Welcome to The Explainer. Today, we're diving into something that's happening all around us all the time, the cosmic dance of chemical reactions. This isn't just a chapter in a textbook, it's the invisible choreography that creates, well, everything. So, let's start with a little puzzle. What do a burning match and a rusting nail really have in common? I mean, they seem totally different, right? But the truth is, they're both doing the exact same thing deep down. They're both putting on a show. A chemical reaction. But how can you even tell when one of these reactions is happening?
And that's our first mission. We're going to learn how to spot the signs. Because before you can understand the dance, you have to be able to see the dancers on the floor. And luckily for us, chemical reactions have some pretty obvious tells.
Okay, first up, one of the most dramatic signs is a change of color. I mean, look at this. You start with this really bright red powder, mercury 2 oxide. You just add a little bit of heat, and boom, it completely transforms into this shiny, silvery liquid mercury. It's a total visual makeover and a dead giveaway that a chemical reaction just went down.
Another way a reaction pretty much announces itself is with bubbles. You know, if you drop a piece of zinc into some dilute acid, it's not just going to sit there. It starts to fizz up. And those bubbles, that's hydrogen gas, a completely new substance being born right in front of you. Here's another one you can actually feel, a change in temperature. If you've ever seen someone mix quicklime with water, you know it gets hot, like really hot. That's what we call an exothermic reaction, because it's literally releasing heat energy out into the world. It's like the dance is so energetic, it's heating up the whole room. And for our last big sign, sometimes you can mix two totally clear liquids together and a solid just appears out of nowhere. It looks like magic. This is called a precipitate. You take clear silver nitrate, mix it with clear hydrochloric acid, and you get this milky white solid, silver chloride. It's not magic, it's just chemistry at its coolest.
All right, so now we go how to spot a reaction, but what are the elements actually doing? Well, that brings us to section 2, the 4 chemical dances. We're going to look at the 4 main types of reactions, and trust me, each one has its own unique style. First on the dance floor, we have the combination dance. You might also hear it called synthesis. This one is the easiest to picture. It's simply when 2 or more dancers or simple substances join together to form one brand new, more complex couple. So the basic move looks like this. You've got dancer A and you've got dancer B. They meet on the floor and they come together to form a single unit, AB. Simple, elegant, and it's how you start building bigger things.
A perfect real-world example is when iron and sulfur get together. You heat them up, and these two totally separate elements combine to create a whole new compound, iron sulfide. 2 individuals become one single partnership.
Up next, we've got the total opposite, the decomposition dance. So if the combination dance is about 2 things getting together, well, decomposition is the dramatic breakup. This is where one big, complex compound splits apart into 2 or more simpler pieces.
And yeah, the schematic is the exact reverse of what we just saw. Our couple, AB, decides it's not working out and they break up, splitting back into the individuals A and B. It's the story of something complex becoming simple again.
Hey, remember that red mercury oxide we talked about earlier? That was a decomposition dance. The compound gets heated up and it breaks right down into its original parts, that liquid mercury and a bit of oxygen gas, a textbook chemical breakup. Okay, the drama is about to ramp up with our third style, the displacement dance. The best way to think about this one is like a dancer cutting in on the dance floor. A new element shows up and just takes the place of another element that's already part of a couple. So here's how it goes down. Dancer A sees the couple BC. Now A is, let's just say, a little more reactive. So A swoops in, steals C for a new partnership, AC, and leaves poor B standing all by themselves. It's all about chemical competition. A classic example of this move happens when you put a piece of zinc into a solution of copper sulfate. The zinc is just more reactive, so it literally pushes the copper out of the way to form zinc sulfate, leaving the copper all alone. Tough break for copper. And now for our grand finale, the most intricate move of them all, the double decomposition dance. This isn't just one dancer cutting in. Oh no, this is a full-blown partner swap. You have 2 couples that meet, and they just exchange partners to form 2 completely new couples. So look, here's the schematic for the move. You've got the couple A, B, and the couple C, D.
They glide past each other on the floor, they switch partners, and they leave as two totally new pairs, A, D, and C, B. Everybody goes home with somebody new.
You can see this happen when you make silver nitrate and potassium chloride. The silver and the potassium just swap their nitrate and chloride partners, creating two brand new compounds, silver chloride and potassium nitrate. It's a really smooth, elegant exchange.
Okay, so we've got our 4 dances. But you might be thinking this is all just random chaos. It's not. There are rules to this dance floor. And that brings us to Section 3, where we learn that it all comes down to who gets to lead, which is decided by reactivity and energy.
For those displacement reactions, the ones with all the drama, the main rulebook is something called the activity series. You can just think of it as a pecking order for metals. An element higher up on the list, like zinc, is way more reactive. It can always cut in on an element lower on the list, like copper. But it never works the other way around. Copper can't displace zinc. The list is law.
And what about energy? Well, some of these dances give off tons of energy, making the dance floor hot. Those are our exothermic reactions. But others do the opposite. They actually absorb energy from their surroundings, making everything feel cold. Those are endothermic reactions. They're literally pulling heat from the dance floor just to make the moves happen.
So, why should you care about any of this? Because this dance is happening literally everywhere all the time. When things react with oxygen, they create oxides, which basically shape our entire planet. That fancy double decomposition dance? There's a special version called neutralization that happens when an antacid calms your stomach. And the decomposition of baking soda? That's what makes your cakes light and fluffy. This stuff isn't just in a lab, it builds our entire world.
And that really brings us to the final thought. Now that you know the signs and you know the 4 basic dance moves, just look around, right now. From the battery powering whatever device you're watching this on to the air you're breathing, what chemical dance is happening right in front of you?